This is part 6 in a series of videos in which I'm attempting to repair an HP9830A desktop calculator. In the previous videos I got as far as cleaning the chassis, getting the power supply working and having a quick look at one of the boards. In this video we're going to actually start testing the microcode generator. With a machine like this there are so many boards in it that it's very easy to get lost in them and not really formulate a plan of action as to how we're going to go about fault finding. If you have watched the previous videos then you'll know that the fault with this is that the display is completely blank. There doesn't appear to be any activity going on within the machine at all. So what I've done at this point is have a look at the circuitry. I've looked at all the schematics, and what I'm going to do as a plan of attack is start off with the microcode generator within the CPU. Now the core of the CPU is the 4 boards that normally sit here. As you can see, I've removed all the other boards apart from the power supply, and all I have here now are the clock board and the microcode control board. The other 2 CPU cards I've removed for the moment. They're not required for the testing I'm doing here. Now of course, because all these boards interact to a certain degree, it is important to realise that certain things will not work without the other boards present. But what I need to do here is just to confirm that the microcode generator is capable of fetching instructions, and by fetching instructions what I mean is fetching instructions from the main system RAM and system ROM rather than just the microcode generator ROM that we looked at in the previous video. So that's what I'm going to be doing in this video, is starting fault finding by attempting to investigate the microcode generator. As I say, everything else is disconnected, the keyboard's disconnected, there are no other cards other than these 2 plugged in and the power supply. I've hooked up the logic analyzer. I'm using it in state mode, so I need a clock, and so I'm using the main system clock. And what I'll do now is start up the logic analyzer. I'll reposition the camera so you can see the logic analyzer screen, and then we'll boot up the HP and see if there's any activity whatsoever. Just to clarify where I have the logic analyzer connected to is, if we look at the schematic, there's a test connector on the top of the microcode card, and that gives us access to this address bus, which is the microcode address bus. In other words, it's the address that's fed into all the ROMs in the microcode generator card, and it's used to select the particular code step in the microcode sequence generator. We also have the input to the latches or the flip-flops that control that address. So in other words, we're looking at the address that's been selected within the ROMs, and we're also looking at the interpreted output from those ROMs. When I say interpreted, these 2 chips allow for modification of the jump address that's going to be selected for the next step in the sequence, and that is variable. It depends on the particular instruction that's being carried out and the status in the rest of the machine. But we'll come back and look at this in a few minutes. We'll get the logic analyzer started up first and boot up the machine and see what we get. Okay, so hopefully you can hear me over the noise of the analyzer fan. This is the configuration I currently have on the analyzer. I have 8 bits set, and I've called those 8 bits C address for current address, and that is the value on the microcode bus. So that's the address that's been selected within all of the ROMs on the microcode card. I've also got 8 bits that I've called N address for next address, so that is the inputs to the flip-flops that control the value that's going to be placed next onto the microcode bus. In other words, the next address that is going to be selected within the ROMs. I also have single bit value, single input I've called bit 0, and that is the output of this multiplexer. And I'll come back to this bit and the next bit in a few minutes. but what I want to do first is just to boot up the machine and see if we're getting what we expect. When we boot up the machine, it should reset to an address on the microcode bus that's on here of FF, so all ones, and that's in response to this power up pulse. It's NPOP, so it's not power up pulse, and this should set all the or reset all the flip-flops. And because the microcode bus is the not Q output of the flip-flops, that means that when we reset all of these, we should get a high on all of these bits. In other words, we should be looking at address 1717 in octal or FF in hex, and we'll see if we get that, and then we'll see where we go from there. If we look at the microcode listing, then this is the boot up address. We'll come back to what all these means if we need to later. The important ones here are the secondary and primary next address values, so these dictate where we're going to jump to once this instruction is complete. The important thing here is this is not the actual address we're jumping to. These are modifiers because these values are XORed with the value that's currently on the microcode bus. That is important to bear in mind because it does make trying to figure out where we're going a bit more difficult to understand. And also I found some inconsistencies in this listing. So here in the second instruction we have the secondary and primary as 8 and 5 respectively, but if we look at the actual code that's in ROM, then it's got 4 and 5 rather than 8 and 5, so I'm not quite sure which of these is correct. I've looked at a few different listings and a few decompiled versions, and there are various inconsistencies here, so it's really a case of trying to figure out which one's correct. So what I'll do first is boot up. We should boot up to an address of FF, and according to this listing we should then jump to FE, and we should then jump to A6, and we'll see where we go from there. So I'll boot up the machine, trigger I've got this set by the way to trigger on a value of FE, so we should trigger once we jump to this second instruction. Okay, so I've got the analyzer armed. I'll now boot up the machine. What we can see here is initially we've jumped to FF, so we've reset to FF, which is exactly what we should do. We've then gone to FE, so if we look at the value for the next address, that's the green trace, you'll see that it's got an initial value of 01, and that's exactly what it should have. So secondary and primary, they're reversed on here. Bear in mind these are in a bit of a weird order, as are the bits within these addresses. So the 0 is the first digit and the 1 is the second digit. The next one, 58, is, and this is what's coming out of the ROM. It's the important thing to bear in mind. So the value we're looking at on the green trace is the value that's actually coming out of these two ROMs. So one digit from one ROM and the other digit from the other ROM, and they're being fed back to potentially be XORed with the current value. So if we look at this, we'll see that the value once we get to address FE, so that is once we have set an address of FE on this bus, these two ROMs then give us out a value of 58. So it's 5 and 8. And if we look at the listing, we'll see that that is correct. We should have 5 and 8, and I think this is wrong, or there's a very consistent error in the ROMs, which I think is unlikely. So it looks like these are correct at what should be 5 and 8, and that's what we have. But the next part is wrong. It's changed to 59, but it's changed after 2 cycles, 2 clock cycles. If I now move across the trace, we'll see what happens after this. So we'll go across, and after a number of clock cycles, firstly we'll see the value has changed to 59. So that's the value here has changed to 59. It was 58 initially, so we had the value coming back from the two ROMs. was 58, but it's now changed to 59. In other words, bit 0 has gone from a 0 to a 1, and what we've now done is we should be jumping to address A6, but as you can see we're actually jumping to address A7. So what I've done is worked out what addresses we should be jumping to. So these are the two instructions that we have. We could ignore this one. I did this to see what the value would be, and it's incorrect. So the top one is the first instruction. This is the encoding for the instruction, and this is the second instruction. So we'll come back to these in a minute. There's an important feature here that we need to consider, bearing in mind the results we've got on the analyzer. But I've worked out the destination address for the values we're seeing. So 58 is correct, and it should take us from FE to A6, but it's not doing, and if we have the other value of 5 and 4, it would take us to AA and not A7. So I did this to try and figure out where the error was in the listing, and it looks like it is just a typo, and this should be 58 and not 54. So now we know we should be jumping to A6. The real question is why we're jumping to A7. The next thing to do is we'll follow through and look at some more of the code that we captured, and we'll see that we're jumping from A7 to 5A and then back to A7. What I'll do, I'll compress this a bit so we can see it more clearly. So I'll do 4 clocks per division on the screen. If I now scroll through, you can see it's just now jumping between 5A and A7. And if we actually look at the value for the next address and then we XOR that, then that is actually correct. If we look at the microcode listing, I won't do it on camera now because I don't want the video to get too long, but if you look at the microcode listing, then the 5A and A7 are actually in part of an in-out routine. And so what it's doing is it's jumping between these two addresses because it's checking one of the flags in the system to see if a particular in-out routine has completed. And firstly, I don't have the in-out card fitted, so it wouldn't complete the in-out. But also, we shouldn't be here. We did not actually jump into the in-out routine as such. What we did is we jumped straight from the reset at FF. We went to FE, and we ended up, for some peculiar reason, with an input for the XOR value of 59 rather than 58. And because that meant that bit 0 was a 1 instead of a 0, we ended up at A7 rather than A6. In other words, we kind of jumped to A7 by mistake when we should be at A6. So the first question is, why is it doing that? What's going to modify that particular bit? So what I'll do now is I'll turn the analyzer off and we'll look at the circuits, do a bit of investigation and see if we can figure out why it's done that and what the potential reason could be. Okay, so we'll do a bit of investigative work to see if we can figure out why the microcode engine would jump to A7 instead of A6 as it's supposed to. What seems to be happening is it's jumping into that particular part of the code and then it's just running round and round in circles and never going anywhere else, which explains why we're not seeing activity in any of the other cards. This is where it's useful to have a good understanding as to how microcode engines work. Fundamentally, they're fairly easy to understand, but their implementations are normally fairly complex because most of the systems support quite a large number of instructions. Those instructions consist of small, in this case, loops of code that fulfill the required hardware steps to complete each instruction. So that is, if we imagine this set of 7 ROMs is just a single ROM of 256 words, each of those words being 28 bits wide, then the data coming out of the ROM, the data bits, are used as the different elements within the instruction, and they are used to control various parts of the electronics within the system, they're used to select the next address within the microcode engine to jump to. They determine how many clock signals will be carried out for this particular instruction. So what happens is, to run a particular instruction, then a small sequence of addresses within this microcode ROM set is cycled through, and as those addresses are cycled through, then various hardware lines change state, and those hardware lines are used to control the different elements within the system. And by running through that sequence, we complete the requirements for a particular instruction. Now, to give the system flexibility and allow it to respond to the different status responses of the CPU and the machine overall, then the way this is configured is we have this microcode address register. So this is the 8-bit register that comprises those 8 flip-flops, and these are used to determine which address is the next one that's going to be selected within the ROM set. But if we look to the left of that, we'll see that we have what they've called a branch condition selector. This allows a modification of the address that's next going to be selected. So in other words, the ROM code set may say, right, the next step is to jump to this address. But depending on what the instruction is that's being carried out, there may be an option for a different address to be selected based on the input to this branch condition selector. So in other words, the destination address for the microcode engine might change based on the status inputs of this selector. And this selector, if you recall, is just a couple of multiplexers. The main one is the 16-bit multiplexer that takes 16 input lines, and then the output is selected based on the instruction that's being carried out to determine whether the destination address should be modified. This is important to what we're seeing. If we go back and look at the schematic, then this is the multiplexer, and the bit that's being changed, it should be a 0, but it's a 1, is bit 0. So instead of it being A6, it results in a value of A7. In other words, bit 1 is incorrect. And we can see this small bit of logic here. This is the multiplexer where the status values being fed into it can be optionally used to modify bit 0 of the microcode bus. However, it's not always used. We have this input here called BRC, and what that does is it allows us to ignore this particular signal and always use the signal coming back, or the level coming back from the output of the ROM. Whether this is enabled or not is dependent on the particular instruction that's being carried out. If we take a quick look at the instruction format for this machine, it is fairly complicated and runs into several pages. This is the basic format, and it's 28 bits. If you count all these, then you'll see there are 28 bits here, and this set of 28 bits is the data that's coming out of the set of ROMs. The one we're particularly interested in here is the BRC bit. So if we get rid of all the extra information in here, we may come back to this another time, but each of these fields can have various values, and the values that are in the fields determines the particular instruction configuration and the effect of each instruction when it's executed. So if we look at a simplified version of that instruction format, we'll see that the PM and SM are the primary and secondary memory values. So these are the values that are coming out of these two ROMs to determine the address that we're next going to jump to. In other words, each instruction will by default have an address that it's going to jump to next, although that can be modified depending on the instruction, and that depends on the value of the BRC field. It's a single bit, and if we look at the description, it says branching enabled. PM will select condition. What this basically means is that we can either optionally modify bit 0 of the destination address based on the status of the line being fed into the multiplexer, again based on the instruction, and that particular input is selected by part of the instruction. So in other words, the instruction contains a field which will select one of these inputs. The output of that is a status line, so in other words we're selecting one of these status lines, and depending on the state of the status line we may or may not modify bit 0 of the destination address. In other words, jump to an alternate address. However, if we look at this code, this microcode set, then we can see that we can actually turn off branching or disable branching. And if we look at this little bit of logic down here, if BRC is set to 0, then it effectively disables this gate. It forces this high, and so this is permanent. This gate here is permanently enabled. In other words, what we end up with here is whatever we're feeding in here, and this is coming from the ROM. So in other words, what we're saying is always use the data coming out of the ROM. So the question first is, in the instruction we're looking at, which if you recall from the listing is this instruction, so it's this value but ending in 85, and the destination should be A6, are we actually allowed to modify bit 0? So I've written this out in binary form, and this is the particular instruction that we're looking at, and it's bit 19 we're interested in. Bit 19 is BRC. If you count the bits up to here, you'll see this is bit 19. If you start at 0, this is bit 19. And you can see in this particular instruction that bit 19 is 0. So in other words, BRC should be 0. If BRC is 0, then we should be looking at the value coming out of the ROM and not the value coming from here. So in other words, there should be no possibility that we're modifying the address for the destination. And so either the address coming out of here is wrong, or this is enabled when it shouldn't be. So what we need to do is look at the value of BRC and see if it is actually 0 as it's supposed to be. BRC is bit 19 of the instruction, and if we look at the second schematic for this card, we'll see these are the other 5 ROMs, and BRC, which is this signal, comes out of this ROM. So it's bit 19 of the instruction is BRC, and this should be 0 for this particular instruction. So I'll get the machine back on the bench, we'll hook up the analyzer again, capture the data again, and see if we can figure out what the value of BRC is. That's the first place we need to look to see if there's an error in the value of bit 0. Okay, so we're looking back at the analyzer screen, and we want to investigate the value of BRC at the point where we reboot the machine and see why it's jumping to A7 instead of A6. Unfortunately, BRC is not taken out to the test connector that we've got the analyzer hooked to. I don't yet have any riser cards for this machine. I've got the boards ordered, they should be here soon, and I'll make some risers up, but for now I'm limited to using the test connector. However, on the test connector there were a couple of spare pins, so I've put a temporary link in from BRC to one of the pins on the test connector, and I now have one of the inputs to the analyzer connected to that pin on the test connector. So what I'll do is add that signal to the waveform display. And obviously I've called it BRC. We now have BRC on the screen. So what I'll do now is boot up the machine. It should go through the same boot up sequence that we saw before. So I'll on the analyzer, power up the HP, Okay, so we've now captured some data, and we have exactly the same thing we had before. It's rebooting to FF, as it should do. The next address modifier is 01. Remember, that's not the next address, that's just what will be XORed with FF, although not in that order. And the value we end up with initially is 58, which is exactly what it should be. So in other words, what we're seeing initially on this address bus, this is the next address input, which is the green, is 58. So in other words, what's initially fed back from here is 58. However, we're then getting that changing to 59. So there's a small delay between the initial address being presented, which is 58, and then it changing to 59. And if we look at BRC, we can see why that is. BRC is high, so this particular line here, which should now be low, if you recall in the instruction, BRC for this instruction should be 0, and yet it is stuck at 1. Because this is stuck at 1, it's allowing the value coming out of the multiplexer, which if we look is bit 0. So bit 0 is connected to the output of the multiplexer. That is 1, and because that is 1 and BRC is enabling the output of the multiplexer to come through and modify bit 0, and what's happening is bit 0 is changing from, when I say bit 0 I mean bit 0 here, is changing from a 0 to a 1, and that's causing the address to change from 58 to 59. Because this next address modifier is 59 instead of 58, then when it's XORed with the current address, which is FE, if we look across to where it's used, then when it's XORed, you'll see that we're jumping to A7 instead of A6, and that's because this value is wrong at 59 rather than 58, and that in turn is wrong because BRC is high. Now, if you recall, BRC comes directly from the output of a ROM. So my first guess would be that this ROM is faulty. Could be that there's a short somewhere, there's something else gone wrong. So what I'll do now, I won't do this on camera because it's a bit tedious and time consuming. I'll have a look at this ROM. I'll need riser cards to go beyond this, so I might have to wait now until the riser cards arrive before I do any in-depth investigation. But I suspect that at least this ROM is faulty and it's giving out a 1 when there should be a 0. So I'll investigate that, get back onto it on the next video and see if we can make any progress.